Good evening, everyone. Welcome to 121st edition of nasscom FAYA Potiti. FAYA Potiti is a monthly technology session hosted by FAYA in association with NASCOM. We aim to create a dynamic platform where tech enthusiasts can come together, discuss, and analyze the latest trends shaping the IT industry. Through these sessions, we aim to foster tech communities that promote peer learning and knowledge sharing. But before we dive into today's session, let's get started with a quick roundup of the latest updates from the tech world. Please join me in welcoming Mishal for the Tech Bytes segment.
So hey everyone, let's start with this month's Tech Bytes, and as usual, we have a lot of AI stuff which is happening around. So at first we have just a minute. Yeah. So we have OmniParser, which is a new, object detection model like released by Microsoft. So it basically, if you upload an image or something, you can detect the, text, logo, buttons, and so on and so forth. Now the use case where it actually happens, right? Just imagine you're using the, Copilot of Microsoft, and you just type a prompt out there, order some, let's say, order a new shoe from Amazon, and just type it to GitHub Copilot. The AI can automatically go open your browser and click the relevant buttons and search boxes and search for Amazon.com and go to Amazon.com and can still see all the buttons and search boxes and images and stuff, and it will detect that automatically and it can order a shoe for you. This is not currently not there, but this is a possibility of this tech, where you can just upload an image and detect all the things which is like just including the small buttons. So that's OpenPassword from Microsoft. Now we have Flux, the new model release, which is 1.1. There are two versions. One is Raw and one is Ultra. Now this is the Ultra, version where they are uploaded. Now with this, they're actually, like aiming to provide 4K hyper, quality content. I mean, image generations, 4K image generations using the Ultra model. And the raw model of Flux is actually used for creating slight imperfections to, mimic the more natural looking images. So that's the two models from Flux. Then we have face model from Kling AI. I'll just show you the video over here. So this is actually a AI generated video. That person over here is a real person. So he just uploaded his photo and he just typed text in the input prompt and type press enter. This video is getting generated. Now with help of this, we can create actually new AI characters with seamless, every frame will be the same image. For example, you can upload your own image to the AI. You can type up from, hey, I'm flying on top of an aeroplane or something, then video gets generated. So that's, yes, this is available. Now, no, it's a model. It's from Hugging Face. So you need to download it and play with it. Or there will be other service providers. You can pay your money and use it. Otherwise, you can download it with your GPU and run it. Now, this is something new. This is from Alibaba. They released a new model called Quen. This is a 32 billion parameter model. It's actually for code generation, and that is a performance on par with ChatGPT 4.0. So yeah, and it's completely faster to ChatGPT 4.0. Yeah. So that's it for this month's Tech Bytes. Thank you. So we are having a film. I mean, there are like a lot of updates on thing, and like the Linux has a new update, the new kernel gets released. So that's an update over there. Do you want to talk something?
I'm just gonna do some talking, I guess. That's my usual stuff. So talking about new stuff that's been happening around. There is like, okay, I'll be talking about more AI stuff. So yeah, this is gonna sound boring for some folks, but I'll keep talking about AI. So over the past few decades, over the past 5 years, let's say, everyone has been betting on scaling compute, basically taking a model, increasing the number of parameters, making the model larger by adding more neurons to it, basically making its brain bigger. That is one thing we have been trying to make models better. That's one thing we've been doing for a long time. But nowadays, the problem is we hit a plateau on improvement. We cannot improve these models by just increasing the number of neurons they have, let's say, the parameters. So yeah, we've hit a, let's say, bottleneck in terms of improvement by pre-training scaling. So yeah, what is the next thing? What is the next thing we can do to improve models performance? So I'll tell you how LLMs work in general. LLMs are just next token predictors. They are just things that will just say a next word based on what you have. That's how ChatGPT and everything works. It's like I am a, and what do you do? It says I am a. The next word is most probably a person, or it might be I am a cat or something else. And how LLMs work is basically once you have I am a cat, it's like oh yeah, is that should I? Okay. So yeah, I'll keep on continuing. So it's like I am a cat. What's next? It just keeps on continuing the conversation. That's how an LLM works. So people have been like one problem that's been plaguing them was hallucinations. That's one thing you got with LLMs. They hallucinate a lot. They just make up things as they write words. So one thing people have been doing to improve its performance was it needs to introspect. And while we write stuff, we also introspect. We like, I'm writing something, and halfway through, while solving a problem, I might be going, hey, something seems wrong, something seems awful. Let me correct myself. You do that stuff while writing some answers. So what these folks did was, okay, what if we try to make that stuff happen with LLMs to improve performance? What if we make the LLM detect it going on the wrong side or it going off the rails? So what they did was in LLMs, basically each token it predicts, they have something called a confidence score, and then they measured it by using, let's say, entropy. So yeah, now the question is, what's an entropy? Entropy doesn't measure much stuff. It just measures the disorder or how spread out these values are. So what they measured was if an LLM is not confident while predicting the next token, they just said, okay, we wanted to make it think about itself, think about the answer it's writing. What if you just put dot 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 to wait in, and surprisingly just works. I just so that's like the new frontier in LLM development. That's just test time compute, they say. Basically making the LLMs write things for longer. You basically make it write dot 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 wait, let me just correct myself, and you just keep on making it write a paragraph of answers and then make it verify its answers. So it might seem dumb, but that's the only way we have for scaling intelligence, let's say. It's not increasing parameter size of these models, like parameters of the models, but instead going for these tricks like measuring confidence scores, measuring entropy, making it generate more tokens, having multiple sampling strategies. So yeah, that, I guess I guess that's one update I have. Then there is something else. Something else is robotics has been advancing a lot. Uh, Recently, Figure. Have you guys heard of Figure robot? You heard of Figure, I guess. Figure. Yeah, Figure recently launched their new robot, Figure 2, and surprisingly, these are getting really, really cheap. You could afford a full humanoid robot for $6,000. It's not that expensive, actually. $6,000, that's like 5 lakhs, right? 5 lakhs, and you get a full humanoid robot, and you could like you literally have that hardware. Now all that you need to solve is basically go to your room, test it out, train a few models, make it deliver stuff for you. Might be might be a long shot, but now people have the ability to tinker with humanoid scale robots at their backyard. It's nice.
Well, I actually saw a Twitter post. So there's an open source human robot. It costs, you can make it from your own for just $300. Just this big from my hand, and it can actually behave like a small human robot. So that's cool. Huh? Yeah, something like that. I just forgot the name, but say for $300 you can create an open source human robot. All the things are open source. You can just build it yourself, and it will cost around $300 something, which is very cheap, and it does provide all the functions of a human robot. Just that it's small.
Thank you, Mishal. Now, without any further delay, let's move on to the main session. Fostering engineering talents, researching complex digital technologies, and sparking innovation in technology solutions. Rajeev Kumaraswamy has done it all. He is a proficient technology solution specialist and currently the director at Cognifluenz Deeptech Private Limited and Inventlabs, two startups that develop innovative tech to solve the toughest real-world problems. It is my pleasure to welcome Mr. Rajeev Kumaraswamy to lead the 121st edition of nasscom FAYA Potato.
Okay. Mm, Not the usual audience, right? I think everybody is having exams. Most of the fifth sem, seventh sem, all the, how are you here then? Huh? Lab exams, okay, fine. Okay, I started very ambitiously when Deeva asked me to give a talk on the subject. But to be frank, I have proven down all of these things, and it's going to be a not so ambitious talk because uh, the technology is actually like almost like an octopus. Now, when you go into one thing, there are hundreds of things coming inside. So I thought that I'll rather stick to some basic things, okay? Because, and then probably during the discussion we'll take up the later things. So we'll just discuss two or three examples. And before getting into those examples, because the language itself is linear algebra. I mean, linear algebra, whatever you already know. So I'll just have a few slides. Each slide will have very little thing written on them. Actually, I have handwritten them. This will be helpful because for the initial portion at least to understand. No, I mean, slides are not. I'm not comfortable with slides when you do the mathematics part. So we'll just spend maybe 10 to 15 minutes if you follow, and then to see whether the language is okay. Then we'll continue.
So before starting, hello? Hello? So, so whenever we have Rajiv here, that is, we will actually have discussions till morning 6 a.m., 7 a.m., 8 a.m. He's very passionate about A, and then the depth at which that is the knowledge he has about each and everything that he speaks is immense. So we have to bring him, and we want to pick his brain to understand certain foundations. So then he was telling like, no, mathematics is the key. ഭൂഗോളത്തിന്റെ സ്പന്ദനം തന്നെ കണക്കിലാണ്. കണക്ക് വന്നു കഴിഞ്ഞാൽ മാത്രം കാര്യങ്ങൾ ചെയ്യാൻ പറ്റുള്ളൂ എന്ന് പറയുന്ന രീതിയിലേക്ക് വരുന്ന സമയത്ത് നമ്മളെപ്പോഴും എ കുറിച്ച് നമ്മൾ വരുന്ന സമയത്ത് we just think about leaves, not about the roots. That is, we have to understand the foundation, what underlying things are there, and then we can connect all those things, whatever we learn. That is, this should act as a session that will help us relate everything to the foundation. Okay, so it is very easy to do a session on LLMs or a session on any of the other technologies, but getting acquainted with the foundation is the key, and it is very rare that we can get some people like that. So make use of this opportunity to make it so interactive. The question should be asked, and it is a very small audience. Just because I didn't want to have a larger audience there, because this should be a open interactive session, and only that core passionate people who actually want to know that should be the participants there. So feel free to ask questions, and then we also have Jiku here. Jiku, you were supposed to be the moderator here along with him, but he just told like that is Rajiv will do that, and then he will be there in the front row to have the active discussion there. Okay, so Jiku is there. Jiku, you can also introduce you.
Uh, Hi, my name is Jiku. I'm actually running a AI company, and yeah, I have been very keen on understanding the mathematics behind it. I, just like you, I'm also very keen to listen to what he has to offer. Thanks a lot. No, I'm very fascinated to hear his perspective on many things that we are actually working on. So I'm a very beginner in most of these things. I would love to actually learn from him.
Okay, thanks for the introductions. But this is going to be very, very, very simple. Okay, so don't worry about the things. So see, sorry about the color and all these things. Okay, means when you look at the mathematics, no, the basic entities that you can think about. The basic means the most fundamental entities is set is something, then any other thing, geometrical point, okay, the numbers, okay. You start with integers or counting numbers, no? These are the primitive things that come. Anything else means, to me, nothing else came up right now. Basic things. So sets, when you work with sets, okay, this is a usual Venn diagram, and then what you have is you can have defined set is a set whatever set theory we discuss is called actually naive set theory, because it's called naive because we assume that a set is a non-thing. We don't define it. That's why it's called naive set theory. If we want to go beyond that, it is actually goes to the foundations of mathematics. It's a very different area. I'm not familiar with it. So once you have sets, sets is simply a collection of elements. So the thing that you can think of is subsets. So you have subsets. So once you have subsets, so you can think about collecting all of them together. So you have a set of subsets. See, there is nothing else that we can do, right? It's a very primitive thing. You have set, you can have subsets, nothing else. Once you have subsets, you can think about operations between them. Okay, if you have two subsets, then what can you do? You can do union, or you can do intersection, or you can do complement of each of them. Okay, is there anything else? Okay, you must have heard about set differences, so many other things. But all of them can be derived from these three. These are the three. In fact, you don't even require, you read only two of them, complement and union. With De Morgan's laws, it will beget you all the intersections. Or intersections and complement is sufficient. So finally, only just, it's so primitive and so simple thing. And if you look at integers, with integers same way, if you have an, you can think about all kinds of things. Okay, if you have 2 and 3, you can add them, right? Or you can multiply them. So these are very basic things. CS students anyway in the discrete math course, they must have covered all these things. So if you have integers and you just consider addition, what things follow? These are the primitive things. Okay, any two integers you take, 2 and 3 or 5 and 6 or 7 and 8 or 127, if you add them, you always get an integer, right? So you say it's a closed, that set is closed under addition. Then if you have any three integers, you can add them in any order. You can first add A and B and then add C, or add A and C and then it won't change. So that's called associative. Then there is an identity element 0. If you add to A 0 to any element, A plus 0 is A and 0 plus A is A. And then there is an inverse. For every integer, there is an inverse when added to the integer. So these are very common things. What do you call such a thing? A set with addition operation, some operation which satisfies these four things. It's called a group. You can have commutative group, so many other things. If you bring in multiplication, then you go to other structures, rings, and then if you take care of the inverse, then you have the field, all these things. So you can have finite and continuous fields, all kinds of things. Theory goes there. So, but what I want to know is, if you have vectors. See, vector. When I say vector, means immediately what comes to your mind is something drawn like this with an arrow, etc. Actually, it's a representation. It's implicit. But without that, we won't begin. So let us begin with that. Suppose you have a vectors, the same way I can think that you can have vector addition. You can, if you have two vectors, you can add them. See, when you say vector, it's always finite, it's bounded vector. It's not infinite length. Okay? Always its magnitude is finite. So if you have two vectors, you can always add them. You will get another vector by the vector addition. Same way you can see that actually it's a group because three vectors can be added in any order. It's associative, and there is an identity element which is zero vector, no length vector. Then there is an inverse which is simply the arrow extended in the opposite direction. So it's a group. So, and in fact it is commutative also. A plus b is v1 plus v2 is same as v2 plus v1. So you say an abelian group. Then if you bring in scalar multiplication, actually you are bringing in something from outside. Scalars are coming from a field. It means if you are not familiar with algebraic field, then you just think it is real numbers. So you have a real number, you can scale the vector. So if you can scale them, a vector v is scaled by a scalar twice 2.5 times or minus 3.5 times or whatever it is. Then there are four or five things, other things. It distributes and all those things. But together, I mean, together what we can do is actually, if you have a collection of vectors, you can scale them and then add them. So we call them linear combinations. Okay. Basically, such a set. It's actually a set of all the 2D vectors. Okay. So if you hope it is visible. So all kinds of 2D vectors. If you take all of them together, you you can you call it as your it's a space with all these properties. We call it vector space. Okay. So the only thing to remember is if you want to formally write down the things, you will write down the conditions for the group, for the commutation, then two distribution things, then the identity in this thing. I mean, it's just another set. So it should be around nine. I think 9 properties are satisfied. Then you say it's a formal thing. But the only thing actually what you should remember and what should you understand is that it's like a safe place where these two operations can be done without any worry. Means set in that set, if you take all the vectors in the 2D with the same, see, you fix the origin and the axis, then you can do all these things without any trouble because you will always get the results. Okay, this is not true the moment you extend it to this summation, you extend it to infinity, then it need not matter. So you always, whatever linear algebra that you come across doing AI or any other, means your practical sciences, or most of them are related to finite dimensional vector spaces. Okay, which means the not only finite dimensional, uh, you actually don't think about sequences of vectors which can go to actually outside the vector space. It can go. See, for example, if you take real numbers, for example, okay, just the set of real numbers. Call it R. So real numbers you write as minus infinity to plus infinity. But is infinity part of the real numbers? It's not part of the real numbers. Infinity is not part of it. Any number as large you want, you can think about, but infinity itself is not. But if you think about sequences on R, real number sequences, that can tend to infinity, right? So it goes outside. It goes outside the set actually. Okay. So same way in vector space also, if you think about operations summations of vectors or of an infinite sequence, then it will be a problem. I just want to, without using any kind of actually writing down equations or anything, let us try to build the basic the basic foundations of the linear algebra. Um, this area is usually studied by writing theorems and proof. But after doing all these things, I mean, what intuition you develop, that is already that intuition you already have because you deal with 3D space. And that's what I'm trying to show. So if you consider a single vector, okay, suppose you have a single vector, okay, from this 2D vector space, okay, and you want to do all those things that are allowed in additions and scalar multiplications. There is nothing to add. There is only one vector, no? So you can't add. You can add it to itself probably, but you can scale it. So you scale it. You keep on scaling it. If you scale it with a negative real number, then it scales this way. So if you collect all the things, it's like you're collecting all the linear combinations, okay, all the weighted sums, starting from this single vector. You start from the single vector, you find all the things that you can create using linear combinations. Then it turns out that they're all in the same line, they're collinear. Actually, this is a one-dimensional vector space corresponding to our 2D vector space. Okay. Okay, so you can say that actually if you start with any one vector, any vector like this, then collect all the things that can be generated from that using linear combinations. Then what you call it is actually it's called span of, that's a word, span of this single vector. So this one-dimensional space is a span. Okay, so quickly we can actually build on this. So suppose I had two vectors, one like this and another. This is the first case. Okay, second case is if you have one vector like this and the second vector also along the same line, let's say v1 and v2. Then what is the span of these two vectors? Same, because they're collinear, isn't it? Because however you add v1 and v2 as a1 v1 plus a2 v2, if you write in the terms of set, say all these things such that a1 element of r and a2 element of real numbers. You take any two real numbers, scale it and add all combinations. For all combinations of a1 and a2, if you scale, you will only get this. Live only. But it's there in the same thing. Yeah, it's there actually. Okay, so now what should I do if I want to span the entire 2D space? You cannot take collinear vectors. So you need to, yeah, you cannot take collinear vectors. You need to take, if you, the first vector is, so if the first vector is taken as, yeah, the first vector is taken in this direction, okay, then the second one should not be collinear, should be non-collinear with the first one. So it can be any angle actually. We can think about this. Obviously, v1 and v2 together. You see that if you add them, yeah, yeah, if you add them, you will get this. But if you add with different a1 and a2, you can get any of these things, right? Using negative numbers also. So the entire 2D space is
should be fine, right? Okay. Okay, now, so with two vectors, one vector like this, one vector can be like this, or you need not take perpendicular. You can take any vector in any direction other than this. So together they will create the entire 2D space. Okay, they will span the entire 2D space. Span is, say, span the entire 2D space. Now, if you want it to span the entire 3D space, what you should do is, if you take three vectors like this, first one, second one exactly like this, and third one in the same plane, then it won't do. Because if all of them are in the same plane, in whatever way you scale or add, the mobile silent lana. Okay. Or I'll use the other one. I'll just use the other one. I'll be careful. Okay. Okay, so even if you have three vectors, it won't span 3D space. The problem is, it's very simple. This third one lies in the span of the other two. Okay, or you can say first one lies in the span of the other two. See, any two you take, they are not collinear, so they will span the entire 2D space. So you have to take the third one away from this. So if you think this is the Z direction and this is the 2D plane, then you have to take a vector, take the third one away from this plane. Okay. If it lifts its head just a little bit away, that's enough. Need not be perpendicular. Anything, so you take the third vector away from this. These two are in the plane. So V1, V2, V3. So you see that what we want is we need three vectors which are, this is non-collinear, this is non-coplanar, so that it spans 3D space. Now, suppose you have three non-coplanar vectors, then how will you add a fourth vector, which is not in the span of the three vectors? Is it possible? In which space it is not possible? Took these 2D vectors as spatial vectors as just as examples because they are very well known. Okay, but these vectors need not be. We are talking about, actually we are not talking about 2D vectors. We are actually concerned with something like this. There is a set V of some entities. We call them vectors. We call them vectors if there is a binary addition defined over them, and there is a scalar multiplication coming from a field. Let's say R here. Okay, this is coming from R. Need not explicitly write it like this. It's actually this multiplication is coming from, there is a field there. So a set of any kind of objects where you can add any two of them and it satisfies group, it's a group, and there is a scalar multiplication defined over them, then we call them vectors. Actually 2D vectors is just one example of those vectors. There are so many other things that you can think about as vectors. A simple thing which will again and again come up is if you have a signal, for example, if you have a signal, continuous time signal t, and you have another signal, let's say this is x1 of t and this is x2 of t. Suppose you have a set of all such signals. Each signal, this is x1 of t, x2 of t. What are the usually most commonly used class of signals in engineering? It's the L2 signals, okay, where the energy is finite energy signals. That is, you square the signal and then integrate, add all of them, then it will be finite. Okay, because we in physically that's only possible. So suppose there are two signals taken, you can add them, right? Point ways. That's what we naturally do, right? We don't think about adding signals. every point, if suppose it is a point at t0, this x1 at t0 added to x2 t0, we'll add them together, right? Point ways, this value add to this value, and we'll get a third signal. Okay. If both the signals are finite energy, then the sum is also going to be finite energy, right? And you can see that actually it's a group, a set of finite energy signals. Any two signals you can add, any three you can add in any order. There is an identity element which is a zero signal, which can be added to any signal, it doesn't change. Then any signal, if you take the ulta, means exact, invert it, okay, the amplitude, then you get the negative signal. So add these two together, you get zero signal. So it's all satisfied. Scaling is very simple. You can scale any signal, amplifying. So it's actually a vector space. Okay. So there are so many other things which are vector spaces. So the whole idea is to use 3D, our intuition, and develop the idea so that we can use it in other places. Yeah. Yeah. It's not. Because here the operations are very simple. Yeah. Addition is simple point based addition. Okay. Eh, uh, yeah. It's not related to that. Scaling operation is not related. Interesting. Yeah. Yeah, they're related, but not this way. Not linearly related. This all linear stuff. Simple addition, scalar multiplication. Not no multiplication between signals. No multiplication between vectors. We don't have. You only have a vector getting scaled using just a number. Okay, so non-collinear, non-coplanar, etc. So if you think about the abstract space, so you don't need to stick to 3 dimensions. So you think that a vector can be taken outside the span of the 3 vectors. So you keep adding. Then this terminology collinear coplanar stops after 3 dimensions. So you have to find something else, and that is called linear independence. Okay. So if you have fourth vector v1, v2, v3, v4, these three we understand whether they are linearly independent or non. Linearly independent means non-coplanar, meaning we already seen the first two. If you take, means the non-collinear means v1 cannot be written as a scaled version of v2. But if you consider all the three, then the third one cannot be written as a linear combination of v1 and v2. Hey, this is the same terminology. We can say v3 is not in the span of v1, v2. It's the same as saying v3 cannot be expressed as a linear combination of v1 and v2. It's the same thing. Okay, it's the same thing. So if you continue on that, it's nothing to do with v3. Like any one of them is. So if you continue like that up to vn, okay. So the condition for them to be the set of vectors to be linearly independent is that none of them, if you take v4, should be expressible as the weighted summation of the others. Basically what it means is, if you take v4, okay, and consider the rest of them, so n minus 1 remaining vectors, so the n minus 1 remaining vectors will span. Span means all kinds of combinations, all imaginable combinations you make, it will span some space. At the most it can span n minus 1 dimension, but it may not if some of them are linear dependent. Okay, so independent means none of them, if you take any one of them, the remaining vectors cannot, we cannot use them to represent them. So each need, that vector is needed there, it cannot be represented by the others. That's why it's called independent. Okay, so now if you continue like this, if you have 4 vectors which are linearly independent, then it will span 4-dimensional space and go on and on. And if you have n vectors v1 to vn, it will span an n-dimensional space. Okay, so here we'll just I don't know whether what I have tried to say is communicated correct. So I'll try to just pick it up. Okay, um, span everybody understands. If there are three vectors, it can span maximum 3 dimensions. If two of them are dependent, then together they will span only 2 dimensions. If one more dependency is all of them are collinear, then it will span only 1 dimension. Okay, so dependency matters. So if you have n vectors, if there is some dependency, then it will span less than n. There is, or each one is independent, then independent means linear independent. There are other kinds of independence, statistical independence, everything. So if the linear independent only means this. Whatever we have discussed, nothing else. Actually, there is nothing more than what I had just mentioned. There is nothing more. Everything is built on top of this. So now, now there is an interesting thing. You have in a 3D space, you know these three vectors: x cap, y cap, z cap, right? Unit vectors, perpendicular unit vector. We are familiar with, from our so many years back we have been doing this, using everything. Why do you use them? There are reasons why you use them. The reason is obvious. I am talking only very obvious things. Why you use such a thing at all? What do you call it? You call it a basis. Okay, basis vectors, something like that. Why you use them is, yeah, okay, okay. Why it's a simple reason is, if you have, this is a three-dimensional thing. It's a three-dimensional space. How many vectors are there? How many are there? Infinite, right? The set of 2D vectors from one origin is infinite vectors. Yeah. Now, how to name them, how to label them, how to talk about it? Okay. You think about it as an infinite set. How will you name them? You cannot. Okay, you can name them 1, 2, 3, etc. That's fine. But there should be a better way of actually representing it in a very succinct way, very efficient way of representing. So this gives that representation, because out of the infinite vectors, we have chosen just 3 vectors out of the infinite vectors. Okay, and with x cap, y cap, z cap, you know that any vector v can be expressed as a x cap plus b y cap plus c z cap, right? Right? Any vector, any arbitrary vector can be represented. Right? This is the representation, right? So there are more to this. It's a very simple thing. There are more things to this. One is that this is unique, meaning if this v is simply a vector. So we have, sorry, we have a vector v, and this is given as this. Since if you change any of this, a is this, b is here, and c is along this direction. Okay, so if you change any of them, a or b or c, the vector is different. You cannot have a, so for every vector, same way, if you choose a, b, c, any three numbers corresponding, there is one point, right? There is only one point. If you use it as vertex, you will get a vector. So there is only one vector corresponding to that. So it's a bijection, you say. The set of a, b, c real numbers, what you call it? Triplet. Simply triplets. Okay. This is the set of all such triplets and set of all 2D vectors. There we can put them in one-to-one correspondence, because for every ABC one triplet there is only one vector. For every vector there is one. So it's a bijection, meaning there is a set here, set here. You put it's one-to-one and one-to. Okay. Okay. So when such a thing happens, in fact, this orthogonality is not required. This is not required at all. Any three non-coplanar vectors you take, you can actually get a complete unique representation. Orthogonality gives us a very additional benefit. What is that benefit? While trying to reconstruct. Okay, now because they are unique representation, instead of vector v, this v instead of that we can use ABC. Usually it is written as ABC or A1B, or I just written ABC. These are the coefficients. Because these coefficients represent only V, I can use interchange them. Okay, just like I use this and say it's a vector. Actually, this is there is a point here, so there is a set of all geometrical points, a set of all such points everywhere, and corresponding to each point there is a vector. So there is all these vectors, 2D vectors. Okay, and corresponding to each geometrical point, you have ordered pairs, A1, B1, right? So these three are actually different sets. Actually, they're different entities. This is a set of ordered pairs, real number. These are geometrical points. These are another abstracting vectors with arrows and all those things. Actually, they're all in bijection between any two. Okay, so that's why we keep on using them as though it's the same. We can use them. When two sets are in bijection, meaning they are one to one on two, we can actually represent the one with the other one. So the same way, that's how we keep on writing vectors. But the catch here is, we write vectors like this. Actually, you can write it like this also. Because actually there is no meaning. Yeah, there is no meaning there is no, it doesn't distinguish. Or you can actually write it as just A comma B comma C. What matters? If you have three numbers, it's actually a three-dimensional vector. But there is something else which is important. Order is important. If you change the order, it's another vector. So basically, it's an ordered triplets or ordered n tuplets. Okay. So the order matters. That's all. Nothing else. It's basically a vector is any ordered set of numbers is a vector. So now some example that I gave earlier looks very simple now. Meaning I gave it as a very profound example. I said the space of signals is actually a vector space. But actually it's obvious. Why? Because if you have a signal, okay. For simplicity, let me take discrete signal. Then we can just think about it. So discrete signal, this is only these values are there, right? Let's say I am taking sample from 0 to n minus 1. Okay, the first sample is x of 0. This is x of 0 up to x of n minus 1, right? They're numbers. So if you write it down as a sequence, you will write a sequence like this: 0.1, 2, minus 2, minus 4, etc., n numbers, right? 6.0. If you change the order between 2 and 4, then the signal is different, right? If this goes here and this goes here, the signal is totally different. So this is also, a signal is also actually ordered set of numbers. If it is continuous, it's a continuous labeling is required. So instead of writing x of 1, x of 2, etc., if it's a continuous signal, usually you index by a continuous index. If it is a discrete, you index by a discrete index again. That's all. Nothing else. Actually, it's a vector, right? So all of them vectors. If in school we actually initially learned this as an example vector, we wouldn't be talking about it here. Unfortunately, we learned everything as separate entities. Okay. See, we went through all these things. Okay. Okay, now just one simple thing. So we close this here. Okay, just because this up to this. I mean, there are 100 theorems and proofs coming in between, but they are all just, actually when you seriously want to study, you have to do them, because I won't be remembering all the proofs, but after years, I still remember all the things. So if you, you keep on forgetting things, but if you do it rigorously, you can always catch up, and you won't have doubt. That's the only thing. Otherwise, this is the only understanding that is to you. Okay. The other things that you need to understand, we will discuss. What are subspaces? What are projections? And then there are there are some important questions in linear algebra, which important from the practical viewpoint. So one we will try to just have a look at. That also you already know, but we'll have a look at it in a different way. So the only two things that are required is basis and dimension from here, okay, from whatever we discussed. Okay. So, so I said that you can keep on adding vectors in a non-collinear, non-coplanar, then fourth one outside. You keep on doing that. So suppose you start with the vector space. So vectors. What is it? It says it's infinite vectors in it. Okay, maybe a n-dimensional space. Suppose it is n-dimensional. Okay, I don't know initially. So I start with one vector. Let's say v1, which is non-zero. Start with one vector. So this is linearly independent, right? This set v1 is linearly independent. There is nothing to check. It's non-zero. It's a non-zero vector. How do you check it? Is this vector should not be represented as a linear combination of the remaining vectors, but there are no remaining vectors. So a singleton element is a linearly independent. Okay. Now what you do, you add one more vector from this. It can take any vector from that. Only thing is it should not be in the same line. It should not be a scaled version of v1. Sorry. So you take v2, this is v1, such a way that this is linearly independent. Okay, and you continue until it is exhausted. Suppose you finally came to n vectors like v1, v2, etc. from vn, and this is also linearly independent. But afterwards, because it is n-dimensional space, there are n vectors which are linearly independent. It will span the entire n-dimensional space. So there is no outside. Meaning every vector has been spanned already. See, until then what was happening is this was spanning, the one vector was spanning one small part. So one dimensional subspace of this whole space. Okay. Then if you have these two, then so it keeps on increasing the span. In 1D, 2D, you can see, first you have a vector, it spans this thing. Second vector comes up, it spans the entire 2D. The third vector comes up, it spans the 3D. Same way, it keeps on expanding. Finally, n vectors, it spans the entire V. Now, there is no way you can add n plus 1 to the vector, because no other choice is there. Every vector is already linear combination of them. So there you have to stop. So this is the maximally linearly independent set of vectors. Now, is it anything sacred? There are n vectors. It's not sacred, because we could have started with any vector, any non-zero vector. So that means there are different ways of choosing such a set. But once it is chosen, there are two good things. One is, because it spans the entire set, we can use it as a basis, just like our x cap, y cap, z cap. The same thing. Same way, any arbitrary vector here can be represented as a linear sum of just n elements. Any out of the infinite vectors, any of them can be represented as. So it's a representation. And what will be the representation? Take the coefficients, weights, and put them as a column vector. That's a representation of the vector. Is it okay? If we understood this much, then it's all already known when we are reframing that you have an infinite, not infinite dimension, but infinite cardinality. I mean, vector space is there. You can choose. You can have your choice of a basis. Okay. Once that basis, if it's n-dimensional, it will have n elements. If it is n minus an element, it cannot span n-dimensional space. You can at the most span only n minus 1. Okay. Now, once you have a basis, what you can do is any arbitrary vector can be represented as a1 v1 plus a2 v2 plus an vn, and those a1 a2 an will be unique. for this basis. If you choose another basis, what will happen? You will have some other coefficient b1, b2, bn, and you will call the same vector. Physically, it's the same vector. The basis is different. You will have another values. Okay, b1, b2, bn. But the vector is same, right? We can change the basis. Okay. Now, but whatever basis you create, all of them will have n elements, right? They will all have n elements, n linearly independent elements. This is fine, right? Okay, so that n is something which is invariant. We call it the dimension of the space, vector space. Okay, so this is the actually the first part of the actually without defining we actually looked at subspaces also. Subspace is like, see, if there is a 3D space and there is a 2D plane which is passing through the origin, it's, if you just consider it, it itself is a vector space. It has a basis, itself is a vector space. Okay. Same way, any vector, n-dimensional vector space can have n minus 1 dimensional subspace, then n minus 2 dimensional subspace, n minus 3 dimensional subspaces, all kinds of, and they are not unique also, because it depends on the basis, depends on what vectors you choose. Okay, subspaces are not unique. Okay, okay, it's like, but the uniqueness is only up to this. It's a 3D space, and you choose the xy plane as the subspace. Okay, this is a suppose a subspace. Then if you have a vector, let's say a vector u, then you can project it onto this space. In this 2D space, it will have a projection, okay, which is an approximate, and this is the error. This is the error part. This is the usually, this comes up everywhere, you know, when you're throwing out things. Okay, when you're taking SVD, everywhere you will, when you want to approximate. Okay, this is how you approximate. Now, suppose, can you tell me another 2D subspace for this? This is the XY plane I have taken as a 2D subspace. Any other plane, no? Any other plane passing through the origin is a subspace, like this. Okay, something passing through, but it should pass through the origin. Then in that space, you can have your two vectors, which will act as bases. Okay, so basically, you throw out all the actual spatial things. You think about in very abstract terms. Okay, by now you should be able to do that. Okay, if you have some signal, arbitrary signal which has n samples, immediately you know that it is sitting in n dimensional space. It may be 64, it may be 1024. Okay, it's a 1024 dimensional space. You don't have to be afraid at all, because if you take any three axes, any t basis vectors, 1024 dimensional space. But if you, how do you think about it? You are taking the 37th and 45th and 125th directions. They exactly act like your 3D. Your intuition acts exactly like your 3D space. So you are comfortable, right? Anything you can do, everything actually works. One good thing about this finite dimensional vector space is, whatever you think will be right. You say it means it never becomes counterintuitive. Everything will be, actually it becomes boring after some time, because everything, there is no counterintuitive things. Okay, I'll probably, after when I look at probability, I'll just give one example of a counter where, you know, we started the discussion, never finished it that time. Just nothing to do with this, but to just give it a flavor of what it means. Okay. Actually, the entire this, if you look at the entire mathematics, you know, what your entire thing, meaning whatever you will look up when you learning AI or any other related subjects, or even quantum mechanics or whatever it is, or 3D or any deep tech things which comes. Most of the time you will be reading only the linear algebra part, which you now know that it's very simple. It's actually, it's very simple. Only thing is, maybe you have to get familiar with some more terms which are used, some concepts. Okay, and the other thing is probability, right? Probability, and I call it statistical signal processing. Okay, statistical signal processing. So same thing. I mean, it's not only the same thing, but it's an extended area. So these are the two things which you require. You may require other things, for example, from information theory or geometry. So many things you require. But the most of the deep understanding is coming from these two areas. Okay, and if you look at them, we have already seen, no, it's actually linear algebra is built upon. Okay, there is a larger thing called algebra, but we look only at linear algebra, that also finite dimensional linear algebra. Okay, even smaller thing. Okay, so there is algebra. You don't have to bother about it. Whatever you already know is sufficient. You don't have to go after all the polynomials and nothing else is required. Actually, only this is required. And then, if you look at it, it's actually built upon set theory. Okay, both of these things, they're built on this. Okay, built means, I say the formalisms. Okay, it's formulated based on the set theoretical thing, and these are not like that. Okay, all the algebra and all these things are not like that. Only from I think 18th century, 17th, 18th century, this kind of abstraction, everything was reformulated in terms of set theoretical things. That's what we call modern mathematics. Okay, entire modern mathematics, the difference between the old one and new one, and computer science students when they learn group, for example, okay, actually it's the finest example or maybe the starting point of this modern mathematics, because group is something where there is a set of elements and there is some operation, binary operation, which we call addition because we are familiar with number addition. But only thing is, those elements with that particular operation behaves exactly like integers and integer addition. That's the only thing. Okay, so it can be anything. For example, rotations, symmetries of rotations. All of them, it's not commutative. So many different things can be thought about as groups. In music also, there is a lot of application of group theory. Okay? Then, okay, that kind of abstraction. So, so that's the only thing that may be stopping you from, getting into those things. Okay, I know the difficulty because if you look at probability and statistics, there are so many books. Okay, so many books are there. So many things, right? You go to any bookstore, you find so many books. So when somebody asked me, last time, who asked me? Akhil, he's not here, maybe his exams. After that Mullen launch on CSSD, he came and he started chatting with me. So then he asked me what book to follow. If you know basics which you already have, for your exams, what you already done, then going again and again and digging at it is actually not useful. I mean, what you actually want to build is some abstraction, and for that I can only suggest one book. Maybe there are other books, but only one book I could suggest. But the thing is, it's not difficult, but you should start, you should start following it. I have around 2-3 slides on that actually, how to start thinking, and then okay, and then on top of this, this is actually probability, and this is actually part of a bigger thing called analysis or calculus. Analysis or calculus. So in analysis, there is an area called measure theory, which is actually very vast. Means I know only a very small part of it. And this is probability theory is actually measure theory itself, just normalized to 0 to 1, nothing else. But measure theory has so many other things. So again, in linear algebra, we started with just addition and linear combination, nothing else. Okay, and we keep on building. Same way, the probability starts building from just just three axioms of probability, which is so simple, right? Very simple, but everything comes out of that. Okay, at some point you have to understand this. That's all. Okay, rest you will keep on associating. By association, you will keep on building. It will look very trivial. Okay, it look very trivial, but this is what it is. Okay, today I'll try to get over that also. Okay, very quickly. Okay, I think the book I didn't mention, right? The book is um, Davison and first name. Forget the first name. I just look it up inside. Uh, Somehow I forgotten. It's such and okay. Second name is Davison. The Stanford University professors. Okay, and the PDF is available. It was available for a long time. Actually, it was not published for at least 10 years or so. It remained as a PDF open, and then only they published. They published it around 2007, around that time they published it. Somehow I forgot. Gray and Davison again. Fine. Okay. Actually, you need to read only the first 100 pages. Rest you can read, but first 100 pages you sit and read. It's at a very abstract level, but that's you will never require. Yeah. Nothing, just a theory, whatever you know. Nothing is required. Basic set theory. 100 pages, if you just sit and spend, leisurely, keep a note and write it down, and keep on. You will not require any other conceptual background for doing anything in this area. You won't require anything. You can go to queuing theory or anything. You will not require anything else. Only thing is, it's an abstract level. Nobody teaches from this book. I mean, nobody, even in IITs or anywhere, nobody teaches this. Okay. I know only one person. He was Utpal Mukherjee. He was a IIT Bombay. Meaning, I don't want to psych you, but it's a very simple thing. Simple book actually. It means simple in the sense, if you get over the abstraction, that abstraction part I will do today. Just 10 minutes. We'll do. Rest of the thing is same. There's Utpal Mukherjee. His credentials are exemplary. He was IIT Bombay gold medalist in BTech gold medalist in electrical sciences. Then he went to MIT um, and he finished his MS. Then PhD in one year or something like that. Then he did DSc in all under Gallagher. You know Gallagher, right? Networking, one of the very giants networking. So then he came back and he was in AT&T Bell Labs. Then he came back and started working in Indian Institute of Science. Still there. So he used to teach from this. All the students who learned under him had no problem, because this is one thing again. Just know that when I start looking at all the AI thing, I am an old AI person. I was working 2007, 8, 9 that time. I was working that time. There was no deep learning. Okay, it was there. Hinton was. I used to see something related to not convolution, some kind of network means some kind of results I used to see when I was trying to do my thesis. But they look very weird, so I never went in that direction, because we had a group in IISc under Shastri in learning and automata in IISc. So these papers used to come, but nobody actually gave a damn to this, because whatever you know as deep learning is simply neural networks, which actually came and went away. There was a great boom in neural networks. All the papers, people, thousands of, not thousands, 10,000s of papers every year was, there were bound volumes, usually in conference, bound volumes will be one volume, right, or maximum two volumes. Neural network conference will have some 4 or 5 big volumes. So many people. And finally, most of them were actually junk, were just using it, getting some result. Because there are thousands of application areas where you can use neural network, you will get some result. All such papers. And then what happened is, to increase the, sorry, I am taking a diversion, to increase the capacity of the neural network, you have to increase the layers. Now everybody knows it. Okay, now everybody knows it. But the moment you keep increasing the layers, then the back propagation whole thing just crashes. Why? Because there will be the cost. See, you are actually optimizing something, right? You're familiar with the neural network, right? There are a lot of neurons connected by the weights, right? So many weights, right? So many weights, so many of them, and each weight you initialize in some way. Earlier it used to be randomly, but now there are better ways. Then what you do? You give the input, you know the desired output, but it is not. So the error, somehow you make a mechanism of using the error to correct the thing. That's the backpropagation algorithm. So you are trying to actually optimize the cost, minimize the cost in some way. So in some high dimensional space, some vector space, this cost will be some vector space somewhere. This cost function will come down and go up and go down and go up and all these things. Okay, so you want to hit this. This is your global minimum. But then unfortunately, on the way there may be a small thing here. So your algorithm, there are so many layers, there's so many minima, not global, so many minima, so many very unusual kind of, in the whole space, the cost function space becomes very ugly. So that training fails. Because if you are in this minima sitting here, how will you go here? You have to actually use something extra. Not the usual learning is all gradient descent. Okay? Gradient descent I always think about as a blind person. I have told you, right? A blind person, suppose he has a ball, something, a diamond, which is or something very precious, and he was airdropped from the plane and he landed on a beautiful lawn like our Rajakad area, that Munnar, that upper sanitarium area, it's all lawns, no trees, just lawns, means meandering lawns. So there are global minima, no, minima are there, then again goes up and down, and that's the area. Suppose he's a blind guy, he landed somewhere, but in that, landing from a parachute is slightly difficult. So this fell off his hand. So it rolls off. Okay. So how will he find it? So he will not go climb up, right? He knows that it will go down. So from there he will try out all the three directions. You're looking at gradients, and then whichever is the steepest gradient, that's the steepest gradient algorithm. Okay, and then you go and you come somewhere, and somewhere there is a small dip. If he finds it, it's good. If he doesn't find it, okay, because of momentum, it might have gone over the top and gone to the even smaller thing. Then he has no way of actually, because wherever he is standing, it's already a minimum. All the gradients are positive, so there is no way he can find out. That's the trap that every training algorithm, come into also. Then what can he do? What can he do? He can actually do many things. He can he can have long calls, that stilt walking, right? Stilt walking. Or this is even difficult situation. He has to actually try randomly now because he has no choice now, right? Or probably if there is some minimum, it's all positive gradient, but some is the lesser of them he can try. Need not work. So randomly meaning you have to randomly try different things like genetic algorithms. You cut it and then change the MSB, change somewhere in the MSB, in that address it goes somewhere else. So somewhere else. So he's actually a blind person now. We cannot see it. Okay. Same way, if suppose the slope is low and it takes a lot of time to walk there, he knows that okay, I walked in this direction, again walking in this direction, so it's actually going along the. Why don't you use a stilts, long legs and stand? So the step size is increased. It's all about training. So most of the things about training he can. Why I don't want to go into that. Why did I come here? Okay, sorry. Came to why did I come to neural networks? Okay. Okay. Hinton's thing. So this I think now by now this story is everybody knows. What this group did was mostly in making the training process stable. In a one sentence, that's what they did. So that neural network again became, yeah, useful. Okay, it is became, and it is very much more powerful because we'll discuss one thing SVM slightly in detail because it's all linear algebra, and you will see that it cannot be scaled. This can be scaled because you can breadth and depth you can extend as much as you want, right? That's why we are looking now.
Connection these people were able to make on what we had discussed. It should be an interactive
I'll answer. Otherwise,
Yeah.
answer
Since
outside.
you were from an era where automatons were the ruling, so
Yeah.
you were from an era where automatons were the ruling thing, right?
Auto?
Automata, like
Auto.
finite automata machines, like that's when you were in your youth and exploring AI, I assume. But from when I started AI and when I work with stuff, it's all neural nets, and I've been fascinated by them because it's scalable, as you said. It is just a universal approximator. But again, the problem is the better the universal approximator is, the harder to know exactly what is going on as well. It's not explainable. So what do you feel about them? Like from an automata standpoint, where you understand things, but it's hard to fit it for your use cases, versus neural nets, where you know it's a black box. You know you can't define each param and what's going on. What do you feel about them?
It's working anyway. And explainability is,
Yeah.
you're bringing in explainability somewhere or other. Black box, even then, even then there were black boxes.
Mm-hmm. Okay, it's an
Meaning
automata.
not in SVM or anything, but not in, yeah, meaning no, in other areas there are black boxes. Okay? Like random kind of things. You always have to live with it, right? No, it's a totally different thing. If something is random inherently, you live with it. I'll just give an example. You have a pendulum. It's a common example. You have a pendulum. You can leave it. It will execute a simple harmonic motion according to Newton's laws. Okay? It's a determinate system. If you know the where, etc., if you forget about the laws, then it will keep on doing it. So in the phase space, it will just go and go and go. Okay? I mean the displacement and velocity. It will be executing a ellipse. Now you know the double pendulum.
Yeah, it just goes.
So instead of that stick, you break it into two pieces and put one more ball bearing there, so that it has two. Yeah.
Yeah, it's okay. Oh, okay. So if you make that simple change, I made it once. It'll totally unpredictable.
Chaos theory, right?
Yeah, chaos, because it's deterministic. It's deterministic chaos. It's determined. Every equation is not, but it's chaos because it's highly non-linear. Non-linearity has gotten. So most of the systems are like that. Okay. For example, your heart. Your heart, on the top of it there is a SA node, sinusoidal node, where the electric pulse is generated. So it traverses around the thing, comes and cancels out somewhere here. Again it creates. But if you look at the interbeat interval, it's chaotic. Okay. And chaos is okay. If the underlying dimensionality goes beyond 12, then it is random. We cannot model it as chaos. It's better to model it as random, because the even chaotic modeling will not give any result.
So
I'm just giving another
okay,
example.
okay.
So yet there are occasions when we have to actually live. Yeah.
Yeah. So as
Roughly.
dimensionality,
Yeah.
what is your rough point? Like, so 12. Do you have a reasoning behind it? Did it? Yeah.
No, it's nothing secret from my memory, because
What experiment?
what I did.
Yeah.
Yeah. Yeah. No. What I did was, you caught me. You knew that I was doing something, and then. But this 12
Okay.
is not my contribution. 12
Okay.
was known roughly, and I found out it corroborates with what I was.
Okay.
What I was doing was looking at the ECG signal long time back.
Mm-hmm.
I don't remember when. ECG signal. So you have the QRS complex, where actually the ventricles contract. You're actually pushing the blood out. Okay, pumping. Okay, that stroke is the QRS big thing. So how do you find the interbeat interval? Is you find the centroid that part of the signal, where the center is of that QRS complex.
Okay.
You find it signal processing wise. You use these things actually. Okay, and find the next one. So you get exact positions of the beats. Then the difference between two beats is the interbeat interval. So that will be if your heart is beating at 60 times per minute. Usually it is 72, right? Suppose it is 60, then every second there is a beat. So interbeat interval is 1 second. Now you invert it, you get 60 hertz. That's called heart rate. Okay, so your heart rate will be hovering around 60, 70, 72, 80. If you're running, it will be 120, like that. Now, the thing is, if you look at heart rate because you are inverting every interbeat interval, you are inverting it. Every interbeat interval space, you get a heart rate. You are estimating heart rate every 1 second or 0.7 seconds, something like that. You can make it uniform, etc.
Like you figure out the instantaneous heart rate at each period.
Instant heart rate. You estimates actually.
Okay.
Now, what do you expect this heart rate to be? Should it be? It's around 72, right? For a healthy person, should it be stable or unstable? What is expectation? If you are healthy, your heart rate should be stable, unstable. Because I asked, right?
My
Because
intuition was it should be
it's a dichotomy. There is either this or that. And since you are all intelligent, the question is not there if it is.
But my intuition states it's stable. Why do you think it's?
Why? You're catching it. It's a long time. Meaning, I'll try to answer it because I don't. Nothing comes to my mind.
Let's go back to the question where it was.
Okay,
How did you figure out 12?
Yeah, basically, I'll just complete this. This should be not unstable. It should be highly varying.
Okay.
Heart rate variability. That's why HRV is there. Your Fitbit, everywhere you have HRV, heart rate variability, and that variability should be there. It should be actually varying as in a complex, actually in a chaotic fashion. Because heart itself is chaotic. Heart is a quasi-chaotic system. Because every time it beats and it comes back, and there is no clock or anything. It's a quasi-chaotic system. So every time it comes and crosses that point somewhere, it's somewhere you are making the thing, it crosses again. Next time it comes, it doesn't cross there. It goes somewhere. Never actually. In principle, it never crosses the same path.
Okay.
Because if it crosses the same path at the same point, there is a intersection point. From there, it can either go this way or that way.
Again,
it's a dynamical system. It cannot do that.
Okay.
Right? So, in principle, but because of other things, losses and everything, it will be happening like this. So when I try to get the correlation, what's the dimensionality? See, there is something we will look at embedding of word embedding will come.
Yeah.
So there, actually the words are actually embedded in a high dimensional space. Okay.
What did you model in these
same way?
spaces?
Here this ECG signal itself, actually HRV signal.
It's multidimensional.
Yeah.
Is the HRV
we
signal
don't know the dimension. It's a single dimensional signal.
Yeah.
It's a time series. But the time series is actually created by a process which is
multidimensional. Okay.
So how to infer the dimensionality of that
original
embedding dimension?
Okay.
Not the manifold dimension, but the where it is embedded.
Source. Yeah.
Then you understand that. So how to guess it? So one way to guess this in this particular case is you take the signal. It's a very simple thing. You take the signal. You assume that it is 4-dimensional. Suppose.
Okay.
So you take the first 4 samples. Okay. See, it's like a system which is churning out things, but somehow its signature will be in there. That system's
the manifold
internal,
match
it will be there.
Okay.
Whatever it's like a person, whatever he says, his character signature will be there. Something like that. But it's better than that actually. It's better. It's a high variable system. So from the single entity you are trying to infer the embedding dimension. So one simple way to do it is there are 3-4 different ways. One I try to do, I did, so I remember now. You take let us say it is assume it is 4-dimensional.
Okay.
So you first take the 1, 2, 3, 4 samples. Think of it as a vector. Come from a 4-dimensional vector. Come from a 4-dimensional space. The samples, you have lot of samples coming out of the heart. Okay, heart rate variable. You take the first 4 and think that it is actually produced by. Actually, it's a single thing. It's a time series. Okay, but we treat the first 4 as your first input vector. Then you take the next 4 or slide it by 2, slide 1, slide, leave 1 and 2, 3, 4, 5 you take. Keep on sliding, you get lot of vectors as a sequence. So instead of a single dimensional sequence, you have a vector sequence. Okay. Now that sequence you try to plot. You can actually plot in the sense you need not see it. Actually, you can plot and you can find the dimensionality of that thing because the manifold dimension you can get.
How do you figure
actually embedding is 4, but how do you find? You can do different things because we expect it to turn out to be fractals.
Okay.
So you can find the fractal dimensions like correlation dimension. This is actually one way of finding the correlation dimension, meaning you find the space filling thing.
And when did you figure out that after 12 it's useless? Like what was your reasoning?
By 12 you are able to predict. That is probably the reason.
Yeah. There are two ways it collapses actually, because it's highly non-linear. It will just diverge and go one thing, so that your entire signal is sitting inside some, because of energy restrictions, it is sitting inside a very limited area. So if it diverges like this, the other one diverges like this, and if you try to predict, it goes beyond that, meaning it has to fall back, right? That's why it becomes chaotic. It has to fall back and back and again and again. നമ്മൾ ചപ്പാത്തി മാവ് ഏറ്റവും എളുപ്പത്തിൽ കുഴച്ചെടുക്കാനുള്ള വഴി എന്താണെന്നറിയോ? നല്ലൊരു പൊങ്ങാനായിട്ട് നീളത്തിൽ കുഴച്ചതിന് ശേഷം നീളത്തിലാക്കിയിട്ട് മടക്കുക. സോ ഇറ്റ്സ് വൺ ഫോൾഡ്. ഇത് പിന്നെയും ഞെക്കി നീളത്തിലാക്കി വീണ്ടും മടക്കുക. അപ്പോൾ 4 ഫോൾഡായി. യു ഡു ഇറ്റ് 64 256 നമ്മുടെ ഓർമ്മയുണ്ടല്ലോ നമ്പർ. അതെന്തായിരുന്നു നമ്മുടെ? ഓക്കെ ഓക്കെ ഇപ്പൊ പോയി. If you do it to 32 times, if you do it 10 times, it has been folds 1024 folds. So it will mix so well. Exactly why when you are you have a hot water, you want to add some cold water, you do this, because churning will create turbulence. What happens to turbulence is exactly same, actually fractals. Turbulence is like a fractal. The four huge things will be there, then it will come out, so many things inside again and again and again and again and again. That's how turbulence comes. So the mixing happens very fast. Okay? So actually I got values around.
So increase the vector that's you take up to 12.
Yeah, keep on increasing, 5, 6, etc. You see that the dimensionality keeps on increasing.
And after 12, what did you notice?
No, in my case it can go up to 12, because I got between 9 and 5 for different patients.
Okay.
Healthy was around 6 or something. I forgot the actual number.
Okay.
But this 12 is, I don't answer 12 by this. 12 was something that was floating around at that time from practitioners.
And your
I found
experiments just found that probably 12 is the limit.
Yeah, after 12 it's useless actually. Dimensional.
People are interested in your joke about 2 raised to 64. You should probably.
It's not my joke actually.
Oh,
yeah, you should tell.
Yeah, since Deepu was talking about an interesting aspect of mathematics, I'll tell you a joke. Joke ആയിട്ട് പറയുന്നതിനേക്കാളും ഞാൻ ഇങ്ങനെ പറയാം. Recently ഒരു engineering problemത്തിന് somebody called me and they ആരാന്നൊന്നും പറയാതെ ഞാനൊരു കാര്യം പറയാൻ പറ്റില്ല. അത് പറയാൻ പറ്റത്തില്ല. അപ്പം basically what happened was they wanted to store sequences of number. It's called a crypto wallet. Probably you know what is a crypto wallet. So there are bits to store it. One crypto wallet bits is 256 bits. So the question that company CEO got from the customer is, shall we take all combinations of this crypto wallet and store it in the database so that it will become easier to verify? The interesting aspect is, I told this story to so many people. Only the people who really understood the mathematics before completing started laughing. He started laughing before that. So I was very surprised. So here very few people laughed. The interesting aspect about this is, the number 2 raised, if you want to store 256 bit sequence in a database, it essentially means you are storing 2 raised to 256 numbers. Just to put into perspective, if you are at 2 raised to 80, somewhere around 70 or 80, I don't remember that number, then that number size, I don't want to say it because you will not understand, but I'll compare it with something in the universe. It is more than the number of atoms in the universe. At 2 raised to 84, this number is 2 raised to 256. It's an outrageously huge number. So the point is, I was asking, see, it is this and the customer and both, that's fine, we will build a bigger DB. And I said, see, there is no material in the universe to do this. No, we will use AWS. And I said, sorry, I'm leaving. So this is the reason. Yeah. I think that is finally what they tried to do. So yeah.
Okay. See, the only
You want to cover today?
yeah, just quickly. Very simple case study. When he was talking to me on the phone, I was thinking, this is a gone case. 64-bit, our address space is 64-bit now in computers. Afterwards, it is not doing. How many years now? More than 10 years, it's 64-bit. Nobody wants anything more. So as soon as he said 256, I thought, okay, it's a huge address space. Nobody is going to build it actually. So these, the only advantage I saw, there may be, I don't know the domain means. What is it? That crypt, like, I don't know the domain. So immediately I thought there is a huge space, addressable space, and your things are going to sit somewhere. No, you cannot even call it a manifold. Only advantage, it's not. The only advantage I was thinking was that it may not be the advantage that you can just throw it randomly. You can throw it randomly. It will not overlap with something else. Something previously thrown will be falling somewhere there, yeah. And you can randomly place it somewhere in the library. It will not be overlapping. You will not, because it's impossible to get the same address. Okay. Let me. This we have discussed. Okay, I'll quickly go through because it's one of the main course. See, in linear algebra, after learning, this is the basics actually. Basics, it is not, it's actually sufficient, I told you. For example, if I teach a 40-hour course, whatever I taught you will take around 10 to 12 hours, and that's the basis. I mean, that, but you already know those things, right? You already know those things. It's only learning in a formal way. And the rest of the things, actually, you look at something called mappings. You have vector space, you have another vector space, you do mapping. We are interested in that because all the processes are actually mapping. You have a message coming in, you have code going out. You have a word coming in, you have a embedded encoded thing going out. These are all mappings. Or you have a communication system, you're transmitting something, you're receiving something on the other end. In between channel complicates it. So it's also a system. So everywhere there is a mapping going on. And if you can model it as linear, then all the linear algebra can be applied. So now, only one thing I want from the previous discussion. The thing is, if you, I said that basis is not sacred. You can choose your basis. Okay. So you have a vector space, you have a vector, you choose a basis, you have n numbers, which we call the vector, the representation of the vector. If you choose another basis, the same vector, physical vector is same, but you have another set of numbers representing the vector. Okay, that's what. So if you suppose you have an n-dimensional space and another m-dimensional space with some basis here, some basis b1 and b2, then n-dimensional space means the vectors will be n vectors. M-dimensional space it will be m vectors, right? M numbers. Now, a mapping, okay, a mapping is simply every vector in this vector space is mapped to something else there. Okay. Can somebody give an example? Okay, any of these examples, channel or any such thing. This is the input vector space, this is the output vector space. So every vector is connected to its output is the other vector. Okay. If both the vector spaces are same size, n dimensional, then we can have the same basis also, no problem. Now this thing, once you fix a basis here, this input vector is fixed. Suppose you took one vector there, okay, and for a fixed basis, this is a, we know the vector values. Let's say 2, 1, minus 1, some vector, and here also you have vector. So this vector is connected to this vector through this mapping. Meaning given any x vector, there is a corresponding b vector, right? That's the mapping. Now, the mapping actually, you can think about this as, that's why I don't use thing. No? I use thing, it's easier for you to understand actually. If you have two vector spaces and there is a mapping, means every point is a vector. Every point here is a vector. So every vector, any vector is taken to its image. The image under this mapping. Let's say this is the transformation L. Okay. Or let me transformation, let's say
A, some transformation. So this x1 goes to some y1, something like that. So if you look at the entire mapping, every point here is mapped to there. So you have all these bundles like things connecting them. Okay. So the entire bundle, there are infinite points here, there are infinite points there. Let us for the time being assume that both are same dimensional spaces. Okay. And let's say it's 1 to 1, 1 to, or it need not be because all of them may not be. It may, the whole mapping may go here. But whatever it is,
this mapping actually is simply this bundle, right? Which vector goes to where? That listing, if somebody can give that list, which vector goes to which vector, 2-column list, then that's the mapping. And actually what I have drawn in this picture, the lines, no, that together you hold together as a bundle, that's your mapping. And what is, if a different mapping means the vector will be going somewhere else. Okay. So the endpoints, if they don't change, physical vector going to the particular physical vector, then that mapping is fixed. Okay. Now, if you want to connect n numbers with n numbers, and with every possible choice, because this bundle can be taken in an arbitrary way, right? Any vector can be, I can send it to any other vector. It's another, I'm considering all possible mappings like this, no? This x vectors connected to y vectors, all possible mappings, the set of all, class of all mappings. Then the bundle can be different things. Okay, each bundle is unique, but there are different. If I want to represent that bundle in a systematic way, what I do is I fix a basis here. See, there was no basis. Once I fix a basis, one particular point here becomes a numerical ordered n tuple. Here also fix a basis, ordered n tuple, and this is the way you can connect. If you give the freedom to change this a1 on m into n numbers, there are m into n, m rows and n columns, m into n numbers, real numbers are there that define the matrix. If you are free to change the number as any real number, then every mapping is captured actually. The entire class of mappings, the entire class of linear mappings are captured by just mn numbers. So actually, just as this n tuple is a representation of that physical vector, once the basis is fixed, this n tuple is a representation of that vector. You take that weights values and connect them. Same way, this matrix is the representation of the physical bundle, the mapping, actual mapping. Okay, this matrix is just a representation. If I change any of the bases, okay, suppose I change b1 basis, these numbers will be different. Numerical values will be different. If I change b2, then these numbers will be different. But the points are not changing. Vectors are not changing. If you change any one of the bases, then these numbers cannot represent. No, this will be different. So matrix will change when the basis is changed. The whole thing changes. So you think of it like this. There is some linear transformation, some system you're designing. There is an input, there is an output, and you want to design the system. Okay, some kind of system, some coding system, whatever it is. Okay, so there are different ways of representing based on what basis you choose. Okay, the only one thing you need to carry from this discussion is that this matrix usually has m into n numbers. If you do the matrix multiplication, it's going to be m into n multiplications and right m into n minus 1 additions. Addition, let us throw it away. Multiplication is more costly. So mn multiplications. That's one thing. Second thing is, if I draw a matrix, if I draw a matrix like this, say 1 1 0 0, multiplying some number 2 3, you know that result, right? 2 3, right? Because it's an identity matrix. You know what it does. Just looking at it, you know that you multiply this 1 into 2, 0 is not going to contribute, 1 into 3. Just inspection. But it's very simple. If I make it a big matrix, see the non-trivial matrices which you come across in engineering, big thousands of parameters. Okay, in CNN and all those things, know what are the matrices? 10,000, 20,000, because the number of neurons in one layer, number of neurons in the layer, you multiply them together, 1,000 to 1,000. That's the number, the kind of matrices that come in. So that's where you require dimensionality reduction there, and SVD comes in. So, but that is one thing. Dimensionality reduction, you need reduction of computation. That is one thing. But more important thing here is that if you write so many things, 3.1, 1.2, 3, 4, 5, like you fill it with all non-zero numbers, and if you look at it, can you guess at what is going on when you multiply? You don't know what goes on. But actually what goes on physically is that there is a vector space and there is a vector sitting here. Okay. When you multiply a matrix multiplying a vector, what happens is this vector is sitting in a vector space, this vector, and you get some other vector in some other vector space. Let us for the time being think that it's the same vector space, because n by n matrix you can think it is in the same, both are in the n dimensional vector. So when you multiply, actually this vector becomes some other thing. This is the input vector, let's say x, this is y, let's say. This is what the matrix does. Okay, a simple matrix like this doesn't change it. Okay, some matrices, if they are um, orthogonal matrices, okay, symmetric orthogonal matrices, they rotate. Okay, they are very well known cases. All the rest do so many things. Okay, some rotations plus something else. But this intuition is important when designing things. So one is this intuition, actually what is happening, then probably you can tweak it. You need not do all the things. If you know what exactly is happening, focus on those areas which are actually matter. Rest of the things you don't do the computation. Something like that will be helpful, right? So you need to know what is happening, but unfortunately this matrix, once you fix, so what can you do? See, you have a choice, because you have the choice to choose the basis. We have chosen some base. Usually the initially whatever you choose will be your 1 0 0 0 0 1 0 0, the what is it called, elementary basis. That's what you usually choose, but that may not be the right choice for this. Okay, this may be in a, suppose it is some vector which is in system is all totally rotated in some way. If you rotate this basis vectors and align with whatever physical phenomena happening, then that expressions will become, the matrix, everything will become simple, possibly. Okay, so what you have to do is choose basis in such a way that the matrix is simple. See, matrix is just a representation depending on the basis. So choose a proper basis, so that, so how to do it is, so there is something called a similarity transformation. Yeah. Actually all the tree will change when the basis changes. Basis. Representation. We, today we are not doing it. We'll continue with we'll actually dig on one thing and work out actually. Then you will not have this. I'm not coming down. Huh. I think we are talking two different things, two different perspective things actually, scenarios, right?
No, it might be wrong. Since the most frequently used words are represented by small words. Think about in Malayalam, Amma is a very small word, or things like that is very small. In English, the most frequent words are very small. The, he, and all are small. Why did we do that? If you have small things as primitives to represent them, then it is easier, efficient. In the other same way, think of it, it's not the same mathematically at all. There is no rigor to this, but okay, similar, okay. Yeah. Okay, then Morse code and also the Huffman's coding and everything. Yeah, yeah. Huffman and Fano. Yeah. So basically, what I think from my intuition is B1 or basis is being chosen in a specific way in which the remaining calculation is going to be easier or whatever or computations. Ju- Just to give you an example. Yeah.
No, it's okay. No, I mean, I don't have many slides, so but I'll just. No, we are looking at in simplest form of an n-by-n matrix. Suppose n is very large. The simplest form, other than all zero or identity matrix, is something like an identity matrix, which has values. Diagonal elements are there. Okay, some values are there. Such a matrix is what it does to a vector is simply scaling by the axis. If you have a vector, suppose x1, x2, x3, xn, n values, x1 is scaled with lambda 1, x2 is scaled with lambda 2, etc. So differential scaling, that's the only thing, it's the simplest thing. You cannot think of even a simpler thing. But to get to this, probably you will have the answer here, okay? What you are talking is same, but here we are looking at one particular purpose is there. That's the kind of optimization, not optimization, actually it's a search like thing, it's not an optimization. It's actually brute force finding it actually. So the question is, such a that A matrix you want to convert it into this form by changing the basis. Okay. Now, if you look at matrix multiplication, simple matrix multiplication. Okay. If you look at matrix multiplication, uh, usually what do you do? A11 into A12, A11 into this plus A22. I mean that's the usual matrix. But the same thing you can compose in a different way. You think of this as columns. First column, second column, etc. Nth column. Okay, and this is your x. So your x1, x2, etc. Now, if you, it's a very simple thing. Okay, what do you do here? The first element here multiplies this, right? Okay, when you do the second row, again it's the first element which multiplies this. Nobody else multiplies this element. So you see that this element is multiplied only with this first column elements. Same way the second element is multiplied only by the second column elements. So you decompose it in a different way. You can write it as x1 into c1 plus x2 into c2. I can think of it as a columns c1, c2, etc., etc. xn into cn. Okay. Now you see that what is it actually this sum? This sum is your final y vector. Okay. So you see that this y vector, the output vector is actually a linear combination of the columns of this matrix. This is the fundamental thing. If you understand this way, unfortunately in our engineering college they don't teach it this way. I don't know why. Okay, this is the simplest thing, and this is the only way to teach. There is no other way to teach. So what it means is you already know the linear independence. If these vectors are n linearly independent columns, then this whatever product you get is a linear combination of n linearly independent vectors. So it will span. It's not span. It's actually it come from n-dimensional space actually. Means it can, if you try different inputs, it can span the entire. If you give us inputs all the vectors, the output vectors will span the entire space. But if suppose one of them is dependent, then it will be spanning n minus 1 dimensional space. It's not onto, it's actually into that mapping. Some that kind of it's very simple. That's why once you understand these things, it is very boring actually, because it is the same thing again and again. It keeps on coming, but fortunately or unfortunately, this is all you need for all your. That's what I found out. Whatever I read up to transformers, you don't require anything other than this. The probability side is slightly more trickier. Means more concepts are there, but this side is very simple. Okay. Now the question is, okay. So what you want to do is you construct a basis in such a way that it is constructed out of the columns of this matrix. So you find the linearly independent
columns. That those and then normalize it, they become your eigenvectors, right? That's the whole process. That's how you find the eigenvectors. Oh, yeah. So, so you get the once you get the eigenvector, then the process is just a manipulation. You know how to represent, how to convert this matrix by post and pre-multiplying, means similarity transformations. Those are just writing down things. It's nothing very interesting, so that you will get to this. Sorry. So once you get a diagonal matrix, it's simply scaling. Okay, so that you know what this we already discussed. And then suppose, so this is my last slide on this thing. Actually, this area itself can be taught with on our SVD, singular value decomposition. The only thing that anybody can read it and understand. If you know, if you come this far, any one of you can read it. It's nothing else. I'll just give the philosophy. So this is what I had talked. If these columns of this your matrix, they are linearly independent, all of them. So you have n linearly independent vectors. You take them, stack them together as the sorry. You do the eigen decomposition. Actually, I didn't tell the details, and you can actually convert this to by pre-multiplying and post-multiplying by that eigenvectors. You get this diagonal form. These two vectors will also change, but you treat it that way. Okay, you can do that. It's a formalism. Suppose you don't have all independent vectors, then you are stuck because you don't have a diagonalization. Suppose it is m is not equal to n, then also you cannot do this. Okay, in those two cases, you start with A transpose. Why you do with A transpose is, if it is an m by n matrix, A transpose will be m by m. It's a square matrix. A transpose A will be n by n. So you get a square matrix. In addition, it's a symmetric, because you transpose A transpose is again A transpose. So symmetric matrix, it's also positive definite in some way, so that it's it's actually diagonalizable. It has eigenvectors, all full eigenvectors. There's many other properties. Okay, so that's why you use them, and you find the eigenvectors of A transpose. You find the eigenvectors A transpose A. This is a procedure. I mean, doesn't mean anything. You stack them together, get UV vectors, and this is the form in which you will convert A to S. You take them back to the other side, you get S. Okay, pre-multiply U transpose A, V will be given the. You find S. What is S? S is a diagonal matrix. But because it is m by n, you may not have the full diagonal. It may end somewhere here or somewhere here, depending on m or n is bigger. But those diagonal elements will be there. Rest of things will be zeros. But we have two things other side, U and V, but they are orthogonal matrices, symmetric, and U transpose is identity matrix. I mean, it's a very this is actually, what does it do? This is your matrix, your complicated matrix. You're decomposing it into three matrix multiplications, a composition of three multiplications. This is just a rotation, this is just a rotation, this is a diagonal matrix. Okay, so the rotation you can make out. Diagonal matrix will give you the scaling thing, so you again come back to the induction. Funny thing is, A transpose always exists. For every A it exists, so this works. That's why instead of going for diagonalization, you go for SVD. Even for n by n matrices, always go and do SVD, because the process is, it will work for everything. Why do you distinguish between them? Okay, so I think I'll skip these things and yeah. Singular value decomposition. Singular values is just like your eigen values. Singular values are actually the eigen values of U and V. They are the singular values. Left singular values and right singular values, and the diagonal. Diagonal is the eigen values. Why the name? Thought about it, but there must be some reason. This is a classical mathematics. It's a very old thing. So finally, why do you use it? Your matrix operation, just like in your CM, wherever it is your that weight matrix. Suppose
reduce it in its processing thing. Then you can apply an SVD, and you will, many of the coefficients will disappear. And among the diagonal things, if one more thing I missed out, these are details. You will align the vectors in such a way that eigenvectors in such a way that the maximum eigenvalue will be on the leftmost and in the ascending order, so that your diagonal elements you can actually throw out the insignificant things. You need to use only the utilities, so you get a better representation, like PCA. PCA is exactly doing that. So do PCA. You can use SVT. You can do SVT, and both are on the same thing. Only thing you work on the covariance. Okay. I think because the time, what happened? I think I missed one slide. I think it's okay. What's the time now? So it's almost 7. So I'll skip this thing. It's the probability part. I think it's okay. We'll skip it and we'll go to 3 quickly. 5 minutes each. We'll go through some examples. This is a lengthy one, but I'll just show only the few things. Supporter. You heard about supporter reflection, right? SVM. Supporter reflection. You heard about. There was a before the deep learning came, SVMs were the means they were as good as any other thing. They were leading actually, especially when the number of data points are small. Okay, then SVM is better. So support vector machine is basically I'm just looking at it for not for regression but for classification problem. Classification problem is you have data and you know that actually they belong to two classes, and you have labeled data and you train it so that later on when some new data comes in it will train it. So first most basic thing is think of a vector space where these data points are. See, data point is finally going to be vector, right? So they are in that n-dimensional vector space. Okay, if your data sample is 12 values, then it is a 12-dimensional vector space, and in that vector space you want to separate it into two classes. So simplest separator is a plane. Okay, why we go for simplest thing? Because computational things. Let us see if it is separable linearly. When you can separate a space with a plane. In a 3D it's a plane. In a 4D it is going to be a 3D plane. You call it hyperplane. N minus 1 time. N-dimensional space you cut with a n minus 1 dimensional object, which is a linear object passing to the 0. I need not be passing to the 0. Okay, that's why we call it hyperplane. If it passes the hyperplane passing through the 0 will become a rough space, but this need not be. It can be anywhere. No, data, you cannot say that data is separated at 0. So this is something like this, and suppose there is, you can see there are filled spots and there are two different kinds of. I should have made it bigger. So in this case, you can see the two clusters are easily separated with a plane, right? No problem. But this plane also separates, right? Perfectly separates, no error. This also. So actually there are a lot of possible hyperplanes which will. So the question is, this is the usual situation, right? You want to find out which is the best thing in under some criteria. So what's the criteria that it will be, and how do you optimize it? That's SVM. This SVM is simply this. Okay, nothing else, just a hyperplane separator. The linear SVM means simple hyperplane. So you define a margin around it, so that you have a plane, but there is a margin beyond which actually this will come to this. There, it hits a vector. Okay, whichever this margin hits, it is called a support vector. That's all. That's a support machine. Because that hyperplane is supported by somebody named it. I think just to make people not come. I also had the same question beginning. So now you choose the hyperplane which has the maximum separation given the data. If new data comes in, this will all go away. So on whatever data you have, you find out which hyperplane has the maximum error margin. Okay. See, there is
So that's all the linear SUMs, which is support vectors. Why maximum margin? Because more resilience to error, nothing else. Okay. Then, okay, this I think we'll go. It's the basically how to write it down, nothing else. It's a simple equation. W is a weight. Transpose is simply because I'm writing it in the vector notation. That's all. Okay, because x can be any dimension. I'm just writing it. So x is a vector. W is also a weight vector. That's all. Otherwise, it's simply wx. So this is a mx plus b line equation of line. Okay. This I think we'll skip all this thing. This it's not. It's okay. I'll come to. These are all just how the distant boundary is found. Leave all these things. Okay. You come to um, a second order optimization problem. Okay. We now come to this. Suppose your boundary is not any hyperplane. It is a very nonlinear object like this. See these red things, they are separated by a. So how do you now what you get to do is either you have to find a contorted object, but such a thing is not easily optimizable because of analytically hyperplane is very simple to optimize. I mean the previous slide show that how it is optimized. If it is a complicated function, optimizing it and the calculus involved is it's like not worth it. So instead what you try is, can you take the whole space and map it to some other space by some nonlinear way so that the clusters are separated linearly like this. It's a ഒരു മോഹമാണ് നടക്കുന്നത്. ഇതിനെ എങ്ങനെയോ മാപ്പ് ചെയ്ത് വേറെടുത്ത് കൊണ്ടുപോയി transformed it so that they're separated. Maybe one or two errors are allowed somehow. Okay, how do you do it? Okay, how can you do it? So this is okay. This is a very interesting thing. Don't look at it, but it's a very interesting thing. Cover is one of the greatest information theory persons. Information theory person, Cover. So his book on information theory is a classic. Cover and Thomas. Thomas is a Tamilian. So what he says is, if you have a non-separable problem, complicated problem, then you simply take and transform it into a high dimensional space. Your original problem is sitting in an n-dimensional space. You transform it to very high dimensional space M. If the dimensionality is high enough with a nonlinear transformation, then almost always it will be linearly separated. It's like the 256 problem. That's why you throw it, it will not going to hit it because it's so vast. This is very similar. Actually, the possibilities are so much, and any nonlinear transformation will take you to the separable thing. It's an interesting thing. It can be proved actually. This is why the SVM works actually. Nonlinear SVM works because of this. So this is an example, but it's okay. I think there is something else called a conductor. We will not go into it. That's why it became important. Because you go to see in low dimensional. Suppose you are working in a 10-dimensional problem. Your vectors are all 10-dimensional. So your multiplication, all this inner products, all these things you take. Your computations will all be 10 multiplications, something roughly of the order of. Suppose you take the whole problem and map it into this or some other high dimensional space, because to make it separable, you made it separable so you can your optimization is working well, but the computation has gone so high. So you have to bring it back. So what you do is, all computation multiplications are basically inner products. Inner product means dot products between two vectors. That's what happened. That's the most important thing. I didn't go into that part because it's not linear algebra. It's actually analysis. Distances, norms, everything comes in. Not because I didn't have time. Okay. So these inner products are simply, see, if you have two vectors a1, a2, a3, an, b1, b2, b1, inner product is ai, bi, sigma ai, bi, a1, b1 plus a2, b2, the summation. Okay. In that summation, it's a linear, means simple multiplication and linear, can't say linear, yeah, linear summation. But if you make it non-linear, probably what you are doing in the high dimensional space can be done with this low dimensional coefficients, but in a if you do a non-linear thing, it's not per se an inner product because it doesn't satisfy the inner product all the properties, but we call it as inner product. and that's what we do. Okay, so we actually don't go to the high dimension space. We manage things here. Okay. Anyway, leave all these things. Just an example. There are two things, two clusters. This is the separating hyperplane. In this case, hyperplane is simply point because it's a one-dimensional thing. Separator is 1 minus 1 dimension, 0 dimension point separates it. So what? So now it is not separable because your separator is one point. Either you can put it here or put it here, but you don't separate them completely because on either side there are the other cluster comes. So what you do is use a nonlinear mapping from 1 to 2D. The easiest nonlinear mapping is x goes to x square. So just do that. So the second variable is this is x square. So it goes like this. There's such a simple mapping taken to just one dimension ahead, made it separated it. Just an example how it works. Okay. Okay. Now this is. I think we don't have to discuss transformers, etc. Just look at the word embeddings part. You know word embeddings, right? Oh, I don't know what happened. I think while I was. What is this? I think when I pasted it on this became just. Oh, I know why. I was working with two presentations at the same time. One is the previous version of the PowerPoint, so so it doesn't understand certain things. Anyway, so word embeddings come right in the beginning. Why it is anybody who already knows about word embeddings and usage in transformers? Huh? Okay, yeah. Word vectors. Okay. See, words are, suppose you have an English word. We are using LLMs, no? So everything is language, the words are coming in. So there is, suppose there is a word, say, what is the word? Machine, okay? So the machine is, this language is not understood by any computer. Computer understands only binary numbers. So how it is done usually in our computers is M. You map it to the ASCII code, corresponding binary number. A machine, M-A-C, each letter you have the corresponding binary code, and you have some standards by which you use them and operate it. But this mapping is actually, machine has a mapping, M has a number, everything put together as a collated thing, concatenated thing. Now there is another thing, let us say, Yandram, that's a Malayalam. Machine with machine word. Let me take man and woman, okay? Man, woman, something, or robot or something like that. So man is mapped to M-A-N, woman is mapped to something else. In this particular case, woman has M-A-N, but if you take something else, no, king and queen, that's the example that usually given. There is something so much similar about their status, where they live, what they do, what they eat, etc. Okay? But king and queen, they map to so different binary numbers, right? Because it is mapped alphabet-wise, letter-wise. But when you come to LLM, such a mapping is, one is it is very lengthy, unnecessary thing. Second thing is it doesn't reflect the meaning, because in LLM we are looking at meaning, context, contextual similarity. So to do that, we have to go for a totally different mapping, and that's the word embedding. So what it does is, suppose I have a sentence, I love learning about machine learning. So you tokenize them, each word, I love learning about machine, etc. Then each word is actually, you can forget this is not important. Each word is mapped to a number, but you can straight away come here. Each word about is mapped to a vector. Okay, each word is mapped to a vector. How this vector is found out is from the contextual information. That's the important thing. It's vector. So it is actually, there is some vector space of this vector. In this case, it is just 3, but usually it's not 3, it's much higher. 512, I think usually, I forgot. Yeah, 768, okay. Yeah. So that's the kind of embedding. I'm just for showing it. So in that space, each word is a point. It has a number. Okay. And another important thing, if I'm wrong, you can correct me. Each word doesn't have a unique number. Depends on the things that you're processing. In that context, it will build its own vocabulary, its own mappings, right? Its own thing. So, okay, this is okay. So you need apple, orange, etc. similar, so they should be nearby. Okay, all all the if there is a word and with the context it is related to other words, they all should come in nearby. That's what they try. So word embedding is that. One second. Word2vec is the one which is used by Google, right? No, word2vec is, yeah, Google. Okay, SIBO. These are the things. There are many algorithms. 5 or 6 or 8, around 8, more than that. 10, around 10 algorithms are there. Glow, right? Used by so many things are there. So let me see if I can. Oh, sorry, I should have done it before. Can connect to the Wi-Fi so that I can run this. In SIBO algorithm, what it does is every word it will look in the center. You have a neighborhood there, it will look for the other words. Or if you have two words, then it's in the context, then it will connect to that. So you're building the context. It can be done the other way around also. You have a word and you look for the neighborhood where the same word is there or a related word is there. If you these are iterations actually. So it runs over all the data, and so I do it 20 times, 100. So running over the data, so that it keeps building. Now if you come below, then you will see what is happening is those weight vectors are being updated here. This is the input side weight vector, because there are 8 input choices and 5 hidden layers. 8 to the 5, 8 to the 5. Output side also same weight vector. And then these things are actually constructed out from the weight. It's actually this is actually these weights. For example, if you look at after it's actually these are the weights actually. Actually it's memory valid. The 5 dimensional weight is sitting there. Two colors because I think so one is input side, other is output side. I think. So you construct your representations, word embeddings here. It will be sitting on some manifold, and then later on will be catch on. So that you don't. So it will be, so even though it is sitting in 760 dimensional thing, actually the manifold will be much smaller because you are reconstructing for every use. Every time you make a vocabulary and then when use. How do you come out of this?
how man is related to king, the same way queen is related. So you can do arithmetically, you can go around the place. So you can add king minus man. There are two numerical vectors. No? So king minus man is a vector. So you add it to man so that you will get the king. Same way you can traverse all. Meaning it will not be exactly accurate because of there will be errors. It's a noisy thing. It's built out of all this data. But more or less, this is how it does things beyond. It generalizes. It does things creatively. Meaning it gives you everything comes from this aspect. Similar words, meaning similar things. If you ask for make it more uh, friendly, or you can actually try that I didn't put. If you look at the same mapping created for German and English, you see that the corresponding words come very. They have the same vector, so it works like that. Anyway, it works. That's why the activity works. This is the last example. This is something that I did. It's a very simple idea. That's why I thought it's based on the vector space. I was working in Nissan, and I think it's recorded. So it's a very sensitive thing. Anyway, in the assembly line, the cars. No? When the car comes out, there's something called a jobs per hour. How many cars come out per hour? It's around 50, 60, 65. Because basically every minute one car comes out. So in Japan, and many other countries, Japan, I know there is a mandatory inspection at the end of the line. After everything is finished, there are certified inspectors who inspect the car. They will do some 25 to 30 actual inspections, opening and closing the door, something like that. They will inspect that, and they will record it, and it becomes part of the certification.
It becomes part of the certification. It's a mandatory thing, and it is a highly respected process. So so what so what happens is it is very difficult to do it, because in about 50 seconds, in 50 60 seconds the next car is coming. You don't have that budget. You have to finish it 10 seconds before that. Okay, it goes. So you have to complete 25 checks. So they do everything to help that inspector, the certified inspector. What they do is, they have a, in our case, there was a surface tab here, and he's hands free to do the things. He shouts out the things. He said next. So the next task comes. The screen is, a big screen is put just nearby. So he looks at the screen and keeps doing these things. If the thing is okay, he says okay. If it is no good, he says no good. Next, back, there are a few commands, around 12 to 15 commands, which he uses to control this thing. And this is recorded, this data goes, and then the rest of the thing, from the surface, it goes to the database, and it is created. Even with this, it was not working well, mainly because you need a speech recognition system. He's speaking and it is right. And that was the bottleneck. Because speech recognition, see, your word okay, that itself takes around 0.2 seconds to utter. No good takes even more. And then it starts, probably simultaneously starts recognition. Recognition takes sometimes up to 0.7 seconds. Your budget is only 1 second, total budget. There's so many other things to do. So you need to do it in 0.1 seconds. So what they try to do is, the speech recognition engine, automotive companies don't make speech recognition engine. They're actually third-party licensed thing. And if you look at speech recognition things, if things become improve even little bit, now everything is gone. No, it's a slightly older now because the deep learning. But whatever it is, the speech recognition things have a huge engine actually, something like this, because there are things which are sitting there, which are acoustic model of your throat, Then the language models comes later. Then the entire signal processing, noise removal, pre-emphasis, voice activity, activity detection, because only when it is detected, otherwise it you know it's a huge pipeline. That's why it's taking this much thing, and you cannot avoid it because there are vocabulary is roughly 10,000 words. You have to make that, otherwise it's not useful. So those people said it's they're optimized. You can't optimize it any further. 0.7 to 0.1. How is it possible? So what I did was I want to bring it to point on. What I did is very simple to understand. The key is that they don't require 10,000 words. They use only around 10 to 15 words. And the rest of the words, maybe some other things in the shop floor, somebody else talking, all of them are in the other noise category. Okay, so basically you are looking for a 12 to 15 class classifier. Okay, and then speech signal. This is not the. This is I just taken from the net. If I say okay, it won't look like this. It will look something. If you so this is you have the speech signal of okay, no good, all these things, and usually I needed to decide on which feature I should use. Means some kind of feature extraction is required, and I chose MFCC because it's always used speech for a quite long time. There's so many other things. So Mel spectrum, Mel frequency capstral coefficient. Capstral means spectrum the other way around. Ulta. There's a logarithm also coming inside. So what I finally came down. This is not. This is just a typical. Just for the namesake. Actually, I came down to 32 by 32 matrix. It's a two-dimensional thing, just like short-time Fourier transform. So 32 by 32 array image. That's the what represents the each word. Okay, and this 32 by 32 array matrix is a actually it's a vector. Matrix is also vector because 32 by 32, 32 to 32,024 numbers in that order. That's all. It's a vector sitting in 1024 dimensional space. That's very simple, right? Because we have discussed so many things. Okay, so each word is there are 12 points or 15 points in the 1024 dimensional space like this. Each point is a word. That's what we have to see. And then I just looked at what are the actual distances. You can compute, right? So subtract one image from the other. Okay, image from the image and square it and take the Euclidean distance. And I found out that most of them are roughly separated enough. They actually, because of noise and all those things, every OK will not look alike, but they will be around a cluster around that. Okay, something like that. Some cluster like that. Then simply a classifier. So CNN was there. Once a CNN is trained, how much time does it take for inference? 0.00 seconds, 0.01 seconds. That's how you solved it. Okay. Probability, it's too much of time has gone in, so I think we'll leave it for another day. If everybody is in there, we can take a, need not be part of the FAYA series or anything, but probability completely will work out. Even linear algebra, we didn't, probability requires a സമാധാനമായിട്ട് പറഞ്ഞു പോകണം. We should stop now. It's beyond time, right? Okay. Okay.
Hello? Yeah. So how was the session? Yeah. Just give some feedback.
It was really good. We did not expect anything coming into this, but it was really great, and we learned a lot of stuff from this.
Pretty interesting ആയിരുന്നു ചില കോൺസെപ്റ്റ്സ് മനസ്സിലാക്കാൻ എളുപ്പത്തിൽ പോലെ എക്സ്പ്ലെയിൻ ചെയ്ത് തന്നതിനും it was easy to understand.
ഞാൻ ഈ സബ്ജക്റ്റ് യാതൊരു ബന്ധമില്ലാത്ത ആളാണ്, പക്ഷേ എനിക്ക് വളരെ ഇഷ്ടപ്പെട്ടു. കാരണം മനസ്സിലുള്ള കുറേ ഐഡിയാസ് എങ്ങനെ ചെയ്യണമെന്ന് ഒരു പിക്ചർ കിട്ടി. ഐ മേ നീഡ് യുവർ സപ്പോർട്ട് ഓൾസോ ഫോർ ദ. ഞാനിപ്പോൾ ഒരു ഓൺടർപ്രണർ ബിസിനസ് ചെയ്യുകയാണ്. എയർലി ബാങ്ക് ആയിരുന്നു, ബാങ്കിൽ നിന്ന് റിസൈൻ ചെയ്തതാണ്. No, actually no way related to all these things. I was into sales and marketing.
കുറെ ഫിസിക്കൽ കൺസെപ്റ്റ് കിട്ടാനും കുറച്ച് ക്ലാരിറ്റി കിട്ടാനും മനസ്സിലാക്കി. മനസ്സിലായിരുന്നു കുറച്ച് ഫിസിക്കൽ ആയിട്ടുള്ള ഏരിയാസ്. അതിന് വൺ മോർ ക്വസ്റ്റ്യൻ മീൻസ് ദാറ്റ് ഇസ് വാട്ട് ഇസ് ദ ഇമ്പോർട്ടൻസ് ഓഫ് ഐഗൻ വാല്യൂസ് ഫോർ എ മെട്രിക്സ്? Physical concept. How can you explain eigen value physically? How given is? Lambda 2. We suppose it's a n-dimensional vector, and we have a matrix which transforms it, and we don't have the. We want to reduce the computation. N is very large. Let's say 10,000, 12,000, something like that. So the matrix diagonals will have lambda 1, lambda 2. Those are the eigenvalues. That once diagonalized, that diagonal will have only n elements which are diagonal. So when you multiply with the vector, x1 is multiplied by lambda 1, and it's the output, first component. Second component is lambda 2. So these lambda 1, lambda 2, lambda 3, if you suppose there are 3 or 4 of them which are significant, rest of them are not significant, small in size, small numbers, then you can neglect them. So you can decide which components to neglect from your signal, right? This makes much more sense when we go to the statistical thing. So the Karhunen-Levy transform or PCA, those things are based on this actually.
Okay, so he will be available here till 6 a.m. Okay, so don't worry about it. Eh? Not once. Eh? Is it once? Yeah, anywhere. Okay. So how many of you are here for the fire potato for the first time? Okay. So this is the 121st edition of Fireboard. Okay. Okay, so we started in 2013, and every month first Wednesdays we used to. Yeah. Okay, so and 7 more Fireboard edited to go. So by 12th anniversary, we will be stopping this, and it should be the way to each campuses as well as companies, because everywhere similar people of similar interest should come together on a frequency and meet it. So that is called learning circle. So we have something called New Learn, that is over 40,000 people across the state in different campuses, and there is also something that is going to happen called creating learning. So anybody can switch on a learning circle with a topic, and people of similar interest can come and meet together. So it is just like finding your girlfriends, not girlfriends. Finding people of similar interest and having topic of discussion everywhere, because there are a lot of interesting topics that is going to happen. Previously it was like, for example, in 2013, 14 and all, we were talking about Angular JS. 15, 16 and all, we were talking about Bitcoin, blockchain and all. So every month one topic, that is fine. But as of now, you know that every week there are new drops from tech giants, right? So that is the pace at which things are changing. And this is a culture of bringing together similar interest people and getting connected and building that network, so that you can also feel confident that whatever you are doing there would be somebody else from some other places that is, I have a connect and I can ask them. Most of the time we always hesitate to do bleeding edge technologies or work on those type of things, only because we might be alone and we do not know what we will do when we get stuck. We get stuck and we do not have anyone. And in Technopark we have many things for cultural events, sports and all those things, but there was nothing for tech people, passionate people to come together. And when I was asking the companies and others, because we also have a consortium of CEOs, nobody was interested to do that, because it will act as something where HRs come there and pouch people. And that happened in 2008 or something, so they were not letting me do that. That is where we just decided, like, inside our office we will start doing something. And we had some workstations here, we just removed it and thought like every month we will have one session, and then if and then we start with tech bites, as you say, and like we should just look into what happened in the last 1 month, just to have a refresher, and then delve into one topic, which is, and then you see like all those people coming here today are those who want to actually ride the waves of a change and then want to understand the foundation of mathematics, right? So only those people came here, and that is the oh, started writing the book. Okay, so that is the interesting part here, and even the discussion starts after the session, because you have to network and you can find many people of your same passion but from different company. You might not have met them if these type of sessions were not there. So breaking the echo chamber, that is what is, that is we are always part of average of people whom we are surrounded with, but only 1 or 2 people will be there like that in each company, and they are always outliers and they will not be accepted by the general public. So what we see, like this is a space where all these outliers come together and be confident that we are not alone. There are a lot of other people who are passionate, and that is how we started, and the journey started for past 11 years, and then now we can proudly say that there is over 10,000 people we have touched over the year, and over, I think a lot of people have 200 plus people who are very actively contributing on these activities and all those things. And I think around 200 plus speakers also spoke in different editions. So 121 editions happened in Trivandrum. There was, I think, around 38 or 40 in Kochi and 40 in Calicut also until COVID. Yep. So thank you so much. So when he was here, when we met him, that is, I just want to bring him for a topic, but I do not know that what he should speak and how can we position. Then he was telling me, let me talk about mathematics. Then I was thinking like, oh, if we talk about mathematics, whether people will come, and then whether people will relate to. When he started with algebra, then he went to vectors. So we were thinking like, okay. So whether all these people are connecting or not. That was, so I was asking Jiku that is just let us make it more engaging. Let's bring more people, because he's very passionate. When he start talking something, then he go to another trajectory, and then he will then he will ask, oh, where did I stop? Then he go back. So having that direction for him is very important. So that is what I told, like Jiku should be on the first there to continue, and I am really happy that everyone enjoyed the session as well as it created value. It is all about value getting created, and it is not just for taking a photograph and publishing somewhere. That is real people coming together, clarifying this thing, and also whatever you learn here should be something that should you keep for the rest of your life. That's anything that you see, you should be able to view it in a different, better angle. So that is what it is, and thank you so much for your session, and I request the committee. Yeah. Yeah. Committee to, yeah. A small token of appreciation. Yeah. So we can officially close the session, and then and yeah.
ഒരു മിനിറ്റ് എടുക്കുള്ളൂ ജസ്റ്റ് ഹോംവർക്ക് ക്വസ്റ്റ്യൻ ജസ്റ്റ് ഇത് ഹോംവർക്ക് അല്ല ശരിക്കും ഞാൻ ഇറ്റ്സ് നോട്ട് റിലേറ്റഡ് ടു ദിസ് ബട്ട് ദിസ് നമ്മൾ പറഞ്ഞതെല്ലാം ലീനിയർ ഓൾജിബ്ര ഫൈനൈറ്റ് ഡയമെൻഷനിലായിരുന്നു. അനാലിസിലോട്ട് ഞാൻ എന്താ പോകാത്തതെന്ന് പറഞ്ഞാൽ അനാലിസിസ് ചെന്ന് കഴിഞ്ഞാൽ മൊത്തം മടുക്കില്ല, ഭയങ്കര എല്ലാം കൗണ്ടർ ഇൻഡക്റ്റീവ് ആണ്. ഒരു സാധനം നമ്മൾ